So I'm going to bring us back to our original number set when we have 7 numbers. And I'm going to talk to you about how to make something called a dot plot. What a dot plot does is it lets you graph data so you can see where the stuff is concentrated. But a key element in that is just knowing how to set up an axis, which a lot of students have a hard time with that. I teach college, and a lot of students are a little rusty. The main thing is do not just take all these numbers, write them, and then draw a line between underneath and say, oh, here's 5.9, here's 6.3, here's 6.26, here's 7.2, here's 7.2. And the reason why is because when you draw an axis, you want to space everything out so it's evenly spaced, and the same distance on your axis means the same amount. So the problem with that is, notice there's only a distance of 0.4 from here to here, and then there's a distance of 0.3 from here to here, and then there's a distance of 0.6 from here to here, and then there's no difference between these two, so there would be no distance. So just to draw an axis that marked those all would not be the way to go. When you draw an axis, you want to think about what's my smallest number, and what's my largest number, and just think there needs to be room on my axis to fit all those. So in this case, we want to make sure we have a number like at or lower than 5.9, and at or higher than 8.1. I tend to think, like most humans, in 5s or 10s. So it's really easy to, instead of getting too worried about spacing it out so everything fits perfectly, I'm just going to make a graph that goes from 5.5 to 8.5. That way I can write things, make a mark at every distance of a half, and then just figure out where my points go. For example, so we're going to go from 5.5 to 8.5. Hopefully I can divvy this up so it works out well. So we're just going to call this 5.0. We're going to call this 5.5. We're going to call this 6.0. I'll make these 0.0 just to keep the decimal. I'm going to make this 6.5. I'm going to make this 7.0. I'm going to make this 7.5. Right here, 8.0. And then 8.5. Now notice I didn't use all the space, but that's okay. Just pretend I didn't do that part. Notice that none of the numbers that are listed on your axis are actually in your data set in the first place. That's totally fine. What you want to do is just find, if you'll notice, from 5.0 to 5.5, we should figure there's about 5.1, 5.2, 5.3, 5.4, 5.5. So the first one we need to get on, actually I didn't even need to start at 5.0 because we don't even have a number until about 5.9. So when I make a dot plot, I just make a dot to represent every piece of data that I have. 5.9, 6.3 is on your graph. 6.6, get it on your graph. 7.2, get it on your graph. Notice I'm not being perfectly accurate about the measurement, but that's okay. We're still going to get the idea about how these numbers are spaced out. Now, here's something to note. We have two 7.2s. On a dot plot, when you graph that, that means you're going to stack another dot on top of the first 7.2. What that does is, as your graph grows, it ends up creating a piling effect, so that height will tell you where the concentration or numbers are. In a second, I'm going to add a bunch of other numbers to this and show you something that's a major concept that we're going to see all down the line. But let's get the other two down here, 7.3, 8.1. So the problem with dot plots is if you don't have a lot of data, if you only have 7 numbers, it doesn't tell you that much information. A major idea in statistics is if there's an average, which in this case would most likely be somewhere between, what do we say, 5.5 is a small baby, 8.8 is a large baby. If you were to take all the babies in the country and take the average of all of them, the reality is that average would probably lie somewhere in the middle, which actually is interesting because even of this data set, our average was 7.2 according to the median and 6.9 according to the mean. So that's probably about where the national average would be. So pretend we were not just keeping track of these 7 babies, we were keeping track of a lot of them. Let's just do this really quickly. There's another 7.2 baby. There's a 6.0 baby. There's a 8.2 baby. There's a 7.7 baby. And not to say that it would always happen exactly like this, but the process that I just did, which is randomly adding points, is probably like if I got on the phone and called a friend at a Nashville hospital and they told me all the babies, their birth weights for babies that came out of Nashville hospital for a year, and I called someone in Tallahassee, Florida and asked for the same data, and someone from California, the same data, and I got samples from all over the country. The reality is some would be on the light side, some would be on the heavy side, but most babies would be on or really close to the average. So what you'll notice about the shape of this is the stacking ends up happening more in the center, because the reality is if there's an average birth weight, more than likely babies are going to be born close to that birth weight. And as you go further and further from that average birth weight, you're going to see fewer and fewer babies that are born that are that heavy or that light. So naturally, you may have seen something like this. It eventually forms a shape something like this. And this is just the first time, but not the only time, that we'll mention the normal curve, or you might have heard the bell curve in the past. It ends up being a huge player in statistics in general. The expectation that data will tend to the mean or be close to the middle number in the set, or most data will be there. And then as you get further and further away, the less likely you're going to see data occurring